Hello again, and welcome to our lecture on the product and quotient rules. Last time, you might remember, we developed some formulas for calculating derivatives. The derivative of a constant function, sums of functions, the power rule. We even did the derivative of the sine and cosine functions. Today, we're going to look at formulas for finding the derivative of products of functions and quotients of functions. And it's sad to say that these formulas are not as pleasant to use as yesterday's or last time formula. We also noticed last time that sometimes you still have to go back to that definition of derivative. But fortunately, in this lecture and the next few lectures, we'll develop really strong, powerful tools for calculating almost all the derivatives you'll ever see. And finally, near the end of the lecture, I'd like to show you a differential equation, a theme that will permeate through this series of lectures. So let's see why you actually need a product rule. Let me show you a very simple example where the product of the derivatives is not the derivative of the product. Let's look at f of x equals x and say g of x equal x squared. So these are two functions, x and x squared. The derivative of x is 1. The derivative of x squared is 2x. So the product of the derivatives is 2x. Now let's take the product of the functions. That's x times x squared, which gives x cubed. And the derivative of that product is 3x squared by the power rule. So the derivative of the product, 3x squared, is not the product of the derivatives, which was 2x. So there must be a different formula for this. And here is the formula. This is called the product rule. And it's, as I said, it's not as clean as some of the other formulas. Let me walk it through. The derivative of the product of two functions, f and g, these functions better have derivatives, they're called differentiable functions, is given by the following formula. The derivative of the product is the first function times the derivative of the second plus the second function times the derivative of the first. Let me say it again. First times derivative of second plus the second times the derivative of the first. There's a proof of this formula. It's in every calculus text, and of course it uses that limit definition of the derivative. The proof is kind of messy and doesn't give you a lot of information as to what's going on. Please memorize this formula. It's a crucial formula for success in calculus. Let's do an example to show how to use it. Here's a product of two functions, 3x squared times sine x. So what's the derivative of 3x squared sine x? Well, it'll be the first one, 3x squared, times the derivative of the second, plus the second function, sine x, times the derivative of the first function. Good. Now let's do those derivatives. So it's 3x squared times the derivative of sine, which is cosine, plus that first function, sine x, that second function, sine x, times the derivative of the first, which is 6x. And so we have 3x squared cosine x plus sine x times 6x. And we could simplify this. We could factor out the common term 3x, and you're left with x cosine x plus 2 sine x. So I hope you see how this formula works. It's not actually that difficult. Now, in that last problem, I simplified the answer by factoring. That may not be the way the answer looks in the back of the textbook. And this is always an issue with calculus and with other mathematics courses. You might come up with an answer, say the factored form of that previous problem, but the back of the book has the unfactored form. So it's not clear which one is better. In fact, they're equally good. In general, should you factor or not? Well, sometimes in applications you have to factor because you want to set the quantity equal to 0, and then you'll have to factor because you're using it for something else. But in general, there is no preferred answer. Not clear at all which one is better than the other. it turns out in AP examinations, they encourage you not to simplify your answers. Leave them unsimplified rather than try to say factor or add fractions and things, because you might make an arithmetic mistake. In college, that's not true. We require students to simplify answers, although often that's not well defined what a simple answer is. But we don't like students to say, leave something like sine of 0. Sine of 0 is equal to 0. So don't leave your answer sine 0. Instead, put in 0. Okay, let's turn to the quotient rule now. What's the derivative of the quotient of two functions? Well, the derivative of the function f divided by the function g is given by this formula. It's pretty scary. It's g times f prime minus f times g prime over the bottom g squared. Let me say it again. It's the bottom function times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Okay? Again, you've got to memorize this formula. It comes up all the time in calculus problems. And of course, in this formula, g better not be 0. You can't divide by 0. I've heard all kinds of methods to memorize this formula. Students have come to me with little jingles and techniques for memorizing this. One of them that I sort of like is if you call low the denominator and high the numerator, it's low d high minus high d low over low squared. D high meaning derivative of the numerator. And then a student recently showed me a Santa Claus formula. The student said, imagine the lower function being called ho, H-O, and then the formula becomes ho d high minus high d ho over ho ho. And of course, you're invited to sing this in the shower sometime. Okay, let's do an example of the quotient rule to see how that formula works. And I'll step through it very slowly. Let's find the derivative of 5x minus 2 all divided by x squared plus 1. Here we go. It's the bottom function, x squared plus 1, times the derivative of the top, minus the top function, 5x minus 2, times the derivative of the bottom function, all divided by the bottom function squared. Now, let's do the derivatives. It's going to be x squared plus 1 times the derivative of 5x minus 2, that's just equal to 5, minus the quantity 5x minus 2 times the derivative of x squared plus 1. Well, that derivative is 2x. All of that divided by x squared plus 1 quantity squared. Now, we aren't through yet. We can simplify that numerator. We can multiply it out to get 5x squared plus 5 minus 10x squared plus 4x, again, all divided by the x squared plus 1 squared. And finally, we can combine some terms here and get a final answer of minus 5x squared plus 4x plus 5 over x squared plus 1 quantity squared. Note the difficult pre-calculus here. There was lots of using the distributive law, multiplying out these polynomials, combining like terms. In fact, there was really only one calculus step here. We just did a derivative, boom, boom, and then the rest of the problem was simplifying that mess that we obtained by taking the derivatives. This is always, not always, this is often the case in calculus. The calculus portion of a problem might be just 1 or 2 steps. And then afterwards, there's a whole lot of pre-calculus to clean up the solution. Let me show you another example that has a nice little shortcut attached to it. Let's find the derivative of the following quotient, x cubed plus cosine x, all divided by 6. Well, you could use the quotient rule here, couldn't you? It's the quotient of two functions. But that bottom function's a constant. So I could actually use the constant multiple rule and move the 6 out to become the fraction 1/6, and then just take the derivative of the numerator, which is, of course, 3x squared minus sine x. So the final answer is 1/6 times the quantity 3x squared minus sine x. The study tip here is, I think, clear. You don't always need the quotient rule. You might observe that you can pull a constant out and then use a simpler rule. It wouldn't be wrong to use the quotient rule here. It would give the right answer, just take a lot more time. Okay, we've developed the derivatives of sine and cosine. We did that last lecture. We now are able to complete the picture and develop the formulas for the derivatives of the other 4 trigonometric functions. Let me show you how you do it. Let's look at the tangent function. How could we find its derivative? Well, tangent is defined to be sine over cosine. That's the quotient of 2 functions whose derivatives we know. So the derivative of the quotient sine over cosine is the bottom, cosine, times the derivative of the top, and the derivative of sine is cosine, minus the top function, which is sine x, times the derivative of the bottom, which is minus sine x. The derivative of cosine is minus sine x, all divided by the bottom squared. Okay, that looks pretty messy, doesn't it? But look closer. What do you see in the numerator? Do you see anybody that looks familiar? That's cosine squared plus, minus minus makes plus sine squared, isn't it? And what's cosine squared plus sine squared? That's our fundamental trig identity. It's 1. So the numerator collapses to become 1. And our formula is now 1 over cosine squared, which they usually write as secant squared. Remember, secant is 1 over cosine. So the derivative of tangent is secant squared. Isn't that nice? Kind of a clean formula. So there are 6 trigonometric functions that we work with in calculus, and they all have derivatives. We now know 3 of them. The derivative of sine is cosine, the derivative of cosine is minus the sine, and the derivative of tangent is secant squared. What about the other 3? Well, here's the list of all 6 derivatives. Let's talk about cotangent for a moment. How would you find the derivative of cotangent if you were stuck, you forgot the formula? Well, cotangent is cosine over sine. Quotient rule. And you would do it the same way I just did the tangent, and you would get minus cosecant squared. How about secant? What's the derivative of secant? Well, that's 1 over cosine. That's a quotient. Use the quotient rule, you get secant tangent, and finally cosecant is minus cosecant cotangent. Again, you're going to have to memorize these. These formulas are all very, very useful throughout our course. Please memorize them. And again, it's unfortunate that those minus signs appear, but that's just the nature of the beast. Some of these formulas have minus signs in them. Fortunately, if you forget some of these formulas, you can figure them out by using the quotient rule. Let's do some examples to see how comfortable we are with these new derivatives. What's the derivative of, say, the function 3x minus tangent x? Well, you differentiate term by term and you get 3 minus the derivative of tangent. I check my memory, that's secant squared. So it's 3 minus secant squared. How about the derivative of x secant x? The derivative of x secant x. Well, I hope you recognize that that's a product of 2 functions, isn't it? It's x times secant x. So I have to use the product rule. So here we go. It's the first function, x, times the derivative of the second function. That's the derivative of secant. What's the derivative of secant? Secant tangent. Plus the second function, which is secant, times the derivative of the first function, and the derivative of x is just 1. That wasn't so bad. And then you could factor out the secant if you wanted to and get a final answer of secant x times the quantity x tangent x plus 1. Good. I think we've got these formulas down. I'd like to now look at what are called higher order derivatives. If you have a function, you can take its derivative using some of these formulas and you get a new function, the derivative. Well, maybe you'll want to differentiate that function again, and you would get what we call the second derivative. Let me show you a very simple example. Let's take the function x to the fourth and apply the power rule to find the first derivative. It would be 4x cubed. Well, that's a new function. I can take its derivative, and I'll get what's called the second derivative. That's denoted f double prime. And there are other notations for the second derivative that I'll point out later. And that would be, of course, 12x squared. Well, I could do it again. I could find the third derivative, f triple prime. That would be, of course, 24x. Well, what's to stop me doing it again? What's the fourth derivative? 24. What's the fifth derivative? Well, now I've got a constant, so the fifth derivative is 0. And what's the millionth derivative? 0. Its function has petered out. It's now 0 forever, all the higher derivatives. So you can take a function and do lots of derivatives if you so choose. Here's a key application of that. Remember our position function of a particle? The first derivative was the change in position. That was the velocity. Well, the second derivative is the rate of change of velocity, also known as acceleration. Acceleration is the rate of change of velocity. Isn't that neat? That's the second derivative of the position function. Here, let's have a little game. Do you see a pattern here? Take the sine function and make a list of its first, second, third, fourth, etc. derivatives. See what happens. Okay, we start with sine. First derivative, cosine. Second derivative would be the derivative of cosine, which is minus the sine. The third derivative would then be minus the cosine. And then finally, the fourth derivative, well, it's minus the derivative of cosine, so we get a minus minus, so the fourth derivative comes back to sine x. Do you see a pattern here? What's the fifth derivative? Well, it would start repeating. What's the eighth derivative? Well, the eighth derivative, of course, would be back to sine x, wouldn't it? What's the 16th derivative? Sine x. I hope you can see that this sort of periodic pattern here. Later on, we're going to see a function with a much more amazing property than this one. It's a function which is equal to its first derivative and its second derivative and its third derivative equal to all its derivative. It's kind of a magic function, and it'll come a little bit later in the course. Let's do an application. Let's do an application to astronomy. You recall that we developed the formula for a falling object last lecture, and it was the position function of a particle that is under the influence of gravity, and we're assuming no air resistance. And that was given by 1/2 gt squared plus v sub 0 t plus s sub 0. And the first derivative, which was the velocity of our falling object, would be gt plus v sub 0, and the second derivative would be the derivative of the velocity, and that would be called the acceleration. And if you see, that's just g. That's that constant that we used, the gravitational constant, g. So we have the position function s, the velocity function v, and the acceleration function a. S, its first derivative, and its second derivative. Well, let's do an application to the space program. You might remember that in 1971, the astronaut David Scott demonstrated that a feather and a hammer fall at the same time, the same rate on the moon. And by the way, the moon has no atmospheres. We don't have any air resistance. And the position function for falling objects on the moon is given by S of t equal minus 0.81 t squared plus 2. The plus 2 means that the falling object is 2 meters, I'm using meters here, above the surface of the moon, and then I drop the object. I drop the hammer or the feather, and that will be its position. At time 0, it's 2 meters above the moon, and then it falls down according to that position function. And here's the question. What's the ratio of the Earth's gravitational force to the moon's gravitational force? Well, let's answer that by analyzing the position function on the moon. The position function was minus 0.81 t squared plus 2. Its first derivative is minus 1.62 t, and the second derivative is minus 1.62. Okay, because the acceleration due to gravity on the moon is minus 1.62 meters per second squared, and on Earth it's minus 9.8 meters per second squared, we can form the ratio of those two numbers, Earth's gravitational force divided by the moon's gravitational force, and we get minus 9.8 over minus 1.62, which is approximately 6. So the Earth's force is approximately 6 times stronger than the moon's. Kind of interesting. Well, the moon's smaller. Good. I promised when I started today's lecture that I'd talk a bit about differential equations. Like, what is a differential equation? It's a pretty simple idea. It's an equation, a math equation, that has some derivatives in it. And the goal basically is, given these derivatives, what is the underlying function? Differential equations play a large, monstrous role in applied mathematics, engineering, physics, chemistry, etc. Students end up taking not only, this is at the university, they take 3 semesters of calculus, or say 4 quarters of calculus, and afterwards the engineers will all take a course in differential equations, and sometimes they'll take 2, 3, 4, 5 courses in differential equations. Our mathematics department at the University of Florida has a whole array of courses on how to solve differential equations. It's big business because differential equations model so much of real life situations, wave motions, heat transfer, etc. I think I might have mentioned early on, early in my career as a math professor at Florida, I worked at NASA, and I actually solved some differential equations using computers up at Langley, Virginia. We were modeling airflow across airplane wings, and we wanted to see how the air behaved as it came off an airplane wing. Fascinating work, and it involved very complicated differential equations. So, that said, let me show you a very simple differential equation, and we'll play with it a moment. We aren't going to get too deep into this, trust me. Let's show, just to practice, that the function sine x satisfies the following differential equation. Y double prime plus y equals 0. Let me focus on that differential equation. That's a differential equation because it's an equation involving derivatives. It involves the second derivative, actually, plus the original function, and we hope it equals 0. I'm claiming that sine x solves that equation. Well, let's plug in sine x. The derivative of sine x is cosine. The second derivative is minus the sine. And if you plug the second derivative in, you get y double prime plus y equals minus sine x plus sine x equals 0. And yes, indeed, sine x works. I verified that sine x is a solution to that differential equation. Can you see another solution? Can you imagine another function that works there? How about cosine? I bet you if you check, cosine also works there. Of course, the game is not so much to verify that a solution works that somebody's given you, but rather, how did we come up with sine x being a solution? that's a deeper question for later. Let's talk about now one of the types of applications that will occur in this course after we've developed all our formulas. It's an application in how to analyze the shape of graphs using our knowledge of derivatives. And in particular, I'd like to show an example where we find horizontal tangents. So let's look at the graph of a fourth degree polynomial, x to the fourth minus 2x squared plus 3. So it's a fourth degree polynomial. It kind of goes up, down, something like that. It's some polynomial. Notice that it's an even function, isn't it? It's an even function because the x's occur to even powers. You can verify that's an even function. It's going to be symmetric with respect to the y-axis. So how could we find out where the tangent line is horizontal? And then we'll interpret as to what that means. Well, let's take the derivative. The derivative would be 4x cubed minus 4x plus 0, because the derivative of a constant is 0. And now let's factor that. Here's a case where you do have to simplify your derivative because we want to factor it. We'll factor out the 4x, and that leaves x squared minus 1, and then factor that to be 4x times x minus 1 times x plus 1. We see that there are 3 solutions to this equation, and at each of those points, the derivative is 0. So what are those points? If x is 0, the y value, plug it back into the original function, please. The y value corresponding to x equals 0 is 3. The y value corresponding to x equals 1 is 2. And by symmetry, the y value corresponding to minus 1 is also 2. Let's look at the picture and interpret our results. Here's the graph of that fourth degree polynomial. It goes down, and then up again forever. Well, we had 3 places where the tangent line is horizontal. The derivative is 0. And those are indicated with little dots on the graph. One of them occurred at 0, 3. That's kind of a little hump in the middle. And then there are 2 points at 1 and minus 1 where the graph has a sort of a lowest value. These low values and high values will play a major role when we go to some of the applications of derivative. We'll try to find the minimum value of a function or the maximum value of a function. It might be applied to find the maximum profit or the minimum amount of materials you need to use to build something. These will all come later when we're finished with our formulas for derivatives. Let me show you one more example before we end this lecture. This is a very pretty curve called the serpentine curve. Its formula is 16x over x squared plus 16. And I'd like to find the tangent line to this curve at the origin. This will be good practice of our quotient rule. So let's get to work. The function is 16x over x squared plus 16. Let's take a derivative. It is the bottom function, x squared plus 16, times the derivative of the top, which is 16, minus the top function, 16x, times the derivative of the bottom, 2x, all divided by the bottom squared, x squared plus 16, all squared. Now, you could simplify this right now if you wanted, but don't bother. You only care about the derivative at 0. The question said, what's the slope? What's the derivative at 0? So plug 0 in right away. And look what you get. You get 16 times 16 minus 0, all divided by 16 squared. Everybody cancels, and you're left with 1. What a great answer. The derivative of that function at x equals 0 is just 1. Wow, how simple can you get? And now form the equation of the line. Y minus 0 is the slope, 1. times x minus 0, and you get the line y equals x. Look at the picture. Here is that serpentine curve. You can see why it has the name, kind of looks like a snake or something. And then we asked what was the tangent line at the origin, and the tangent line is the line y equals x. At the origin, this snake-like curve looks very much like the line y equals x. Great. We've seen lots of rules so far. Next time, we'll talk about the derivative of a function that is formed by the composition of two other functions, like the function 3x plus 5 to the 50th power. We'll learn how to find that derivative. Thanks very much, and see you next time.